All right, kiddos, let's do an example here. So we've got a high-speed train traveling at a speed of 44.7 meters per second when the engineer sounds the 415 hertz warning horn. Okay, so far we know that the train is moving and it is the source of the sound. It gives us the speed of the sound. What is the frequency and wavelength of the sound as perceived by a person standing at a crossing when the train is approaching? Okay, so the person, the observer, is standing still. Okay, so we've got our equation, which is moving source. Right, our moving source equation is perceived frequency equals emitted frequency times v over v plus or minus the speed of the source. Okay, so in this we've got the speed of the source is 44.7 meters per second. The frequency, the true frequency, is 415 hertz. The speed of sound v is 343 meters per second. And we're looking for the the perceived frequency, and we're also looking for the perceived wavelength. Okay. And that's when the train is approaching. Okay, so the observer is standing still, the train is approaching. So as the train is approaching, it's emitting sound while kind of catching up to the sound waves that are just emitting, and we're perceiving a higher frequency sound. So that means we want to maximize that fraction. So to make that fraction as big as possible is we want to minimize the denominator. Small denominator means large fraction. So that means we're choosing the minus option here. So we've got 415 times 343 over 343 minus 44.7. Okay, so that means our perceived frequency is 477 hertz. Okay, our math did what we expected it to do, which was make the perceived frequency larger than the emitted frequency. Cool. All right, now we need to know the perceived wavelength. I'm going to do this in a different color. We know that speed equals wavelength times frequency, right? No matter what, the speed of sound in air is staying the same at a given temperature. So we can write this as emitted wavelength times frequency, or include the primes, because the ratio of, or the relationship between speed of sound in air, perceived frequency, and perceived wavelength will be the same. So let's solve this for v over perceived frequency. And that's just 343 over 477. And I believe that's like 0.72 meters. Right, sound waves are long. Big ones. So that's how you would go about that calculation. Okay, so it's easy. It's a matter of plug and chug. But when you're just given an equation like this, it's the conceptual understanding that leads to the correct answer is the tricky part. Okay, when the train is driving away, we've got the same information, except we know if the train is driving away, perceived frequency is equal, we would use v over v plus the speed, right? Because we know when the train is driving away, the perceived frequency will be lower. Those wave fronts would be further apart. And to get a fraction that is the smallest it can be, we want to have a big denominator. All right, so when you do this, 415 times 343 for 343 plus 44.7, right, you should get 367 hertz as the perceived frequency. Okay, just plug and chug. All right, the last thing with regards to the Doppler effect that a lot of people are interested in is the creation of sonic booms. So a sonic boom is the sound associated with shock waves created whenever an object traveling through air travels faster than the speed of sound. Okay, they generate enormous amounts of energy and make a sound like an explosion or a thunderclap. So for example, if you were in class, someone asked about this equation. Right? What if, like, this airplane was moving towards you? Right? Then instead of plus or minus, you would use a minus. And if the plane was traveling at the speed of sound, then the denominator in this fraction would be 0, and that fraction would be undefined. So essentially, when you have an undefined Doppler effect equation, you get a boom. Okay, so this is actually what it looks like. If you ever attend an air show, sometimes they have fighter jets that can travel at or above the speed of sound, and they'll make these things behind them. This is called shock cones, typically. And it's just a bunch of really super compressed air so that it looks like a cloud. So that just happens when you're traveling at or more than the speed of sound, right? Those high pressure wave fronts are all overlapped on top of each other. So you've got a high pressure wavefront on top of a high pressure on top of a high pressure wavefront. And that just makes a really high pressure region. And when you compress a bunch of air together, it becomes cloud-like in appearance. And so this is what it looks like. When that high pressure, the edge of that high pressure region passes you, all of those, instead of hearing a frequency of sound, you just hear a boom. Okay, so here's kind of a graphic here. We've got a jet going at the speed of sound. Right, so right at the back end of the jet, you see the overlap of all of these waves, the wave fronts. If you were a person standing right here, you would still experience separate wave fronts that were still really close together. So you wouldn't experience a sonic boom right there. But if we now have a plane that is going faster than the speed of sound, those wave fronts would overlap. So the speed of sound is less than the speed of the source. If you were standing right here again as an observer, what you would see is all of these high pressure regions overlapping on each other, making a very high pressure region, and this is the shock cone. And when this boundary that I've drawn in here goes by, that's when you would hear a boom. All right, so let's take a look at that simulation. Okay, so up here we've got a back observer and a front observer and a source moving towards the front observer, and we can kind of see that in the direction of motion, those wave fronts appear to be closer together because the source is moving in the direction of those wave fronts. But what if the source is moving at the speed of sound? This is what it would look like, right? Where those wave fronts continue to kind of build up at the source, and it becomes higher and higher pressure, and it kind of creates a kind of a cone sort of deal. And depending on how far you are away from the source at a certain point in time, you might experience some of that high pressure region. Okay, and then here is the source moving faster than the speed of sound, and you'll see observer 1 and observer 2. Notice there will be a little boom that shows up, right when that kind of the edge of that shock cone hits the location of the observer. Boom, boom. Okay, cool. And that is attached to the Canvas page if you want to play around with that as well. All right, kiddos. So here's your homework. There are some problems. What we've talked about so far today was in section 9.5. That's also where you will find the equations in the data booklet for the Doppler effect, right? There's the moving source and the moving observer equation. You'll also find a third equation under the Doppler effect, and that's for the Doppler shift for light. It looks different because the physics is slightly different than light, and we'll cover that when we talk about light in general in our next unit, okay? So take a look at section 9.5. That's where derivations for the other equations are that I didn't do in class, and there are a couple of problems at the end of chapter 9. If you want to try a couple more problems, check out Cutnell and Johnson. I've listed a couple that are at the end of chapter 16. All right. Next class, we'll be working on reviewing for waves, simple harmonic motion, and sound test. I'll post kind of some IB problems that you can consider when reviewing for that test. Our test will be on Monday, which will be the day that is scheduled for our final exams. The final exams won't be any different than our normal class periods in scheduling and length. We don't have a special final schedule. We are being told to not give any asynchronous lessons other than studying for the exam if we're given one, and there won't be any asynchronous lessons during finals week. So you're only on the hook for morning classes, which might include some sort of exam. We're just doing a unit exam. Should be about the same scaling, like around 30 points as our other unit exams. Okay, it will assess all of the topics that we've covered so far. The waves topics are really oddly arranged, and so I've tried to group them. This test will assess 4.1, 4.2, 4.5, and then 9.1 and 9.5. And we'll move on to light in our next unit, how wave properties apply to light. All right, see me during asynchronous. If you have questions, don't forget to submit your IA proposals and your lab corrections, and let me know if there's anything that you need. All right, kiddos, have a great week. I'll see you next Monday. I'll post the test, but please show up to the class meet just so I know that you're around. All right, kiddos, bye-bye.